we live in exciting times. Our leadoff speaker today is Dr. Marco Lanzagorta. Marco is a research physicist at the Naval Research Laboratory. Okay. And he received his PhD from Oxford University in the UK. He's the author of over 100 publications, including several informative books that I have on my own library shelf and have studied them, not as diligently as he'd like, but you know, you do what you can. And truth be told, Marco is the intellectual force behind today's colloquium and has been my physics mentor for over 10 years. So in leading off, his talk will be on envisioning the future of quantum sensing and communications. And I might remind everybody that this is an unclassified presentation, so taking notes is possible. Thank you.
Thank you. Well, first of all, I want to thank Joe for the opportunity of being here. So I'm going to talk about how I see the future of quantum sensing and communications. But before we take a look at the future, I want to take a quick glimpse into the past. And I think the images speak by themselves. Arguably, in World War II, Japan was strategically surprised by our scientific and technological developments. For example, for the Battle of Midway, we could say that part of our advantage was our new developments of cryptographic methods and new ideas in information theory. And certainly the final defeat of Japan came thanks to new ideas and technology that came from subatomic physics. So now, as Joe was mentioning, today we are in the middle of this incredible scientific and technological revolution that it actually combines these two areas of research, information science and subatomic physics. And this is what we call quantum information science, which is basically how to harness quantum phenomena, in particular entanglement, as Joe had mentioned, so we can acquire, represent, encode, process, and transmit information better than what can be done with classical means. As some of you may already know, a couple of years ago, the Chinese, they launched a satellite called the Quantum Experiments Space Scale. And with this satellite, they are able to do quantum teleportation, transmit entanglement. Tanner will go into the details of what means entanglement later on. And part of this, they can also do unconditionally secure communications between two ground stations. So this is, by all means, this is a huge leap in terms of the scientific and technological side of quantum information technology. So some people may say that this is sort of equivalent to the Sputnik, but I would say it's more equivalent to this, which is not a bakery or anything, because you can see the bricks, but it's actually CP1, the first nuclear chain reaction that it was done during the Manhattan Project. And indeed, we have reason to believe that quantum information, it may be considered as the atomic bomb of the information era. And even though this satellite is just doing very simple, well, inside quotes, communications and distribution of entanglement, really what we have is that they have a platform where they have been developing and testing crucial quantum technologies that they could be easily transitioning to potentially disruptive intelligence and military systems. As Joe mentioned one time to me, part of the appeal of quantum sensing and quantum communications is that they are two technologies that can be readily weaponized, in contrast to, for example, quantum computation. So in this talk, I'm not interested in discussing the quantum information technologies that we can build today. For that, our speakers later in the day, they will be talking about what it's been done today. Instead, what I want to do is to try to explore what lies ahead, beyond the horizon. In particular, what are the limits of the possible, making reasonable research and development assumptions, and of course, without breaking the laws of physics. And the reason why it should be valuable, this type of exploration, is because we could avoid to have any future strategic surprises by our adversaries. So the way to proceed is by subscribing to the Clarke's laws, which is a set of laws that help define how to consider claims about the future of scientific developments. And they were developed by Arthur C. Clarke, who is this famous science fiction author, better known for being the writer behind 2001: A Space Odyssey, probably the greatest science fiction movie ever made. And also, he's the first proposer of the idea of satellite communications. So this shows that sometimes to have imagination, it pays off when you try to envision the future. So the second law of Clarke, it says that the only way of discovering the limits of the possible is to venture a little way past them into the impossible. And my favorite, the third law, it says that any sufficiently advanced technology is undistinguishable from magic. So, looking beyond the horizon, probably most people is aware of quantum information in the context of quantum computation and how quantum computers can break RSA, for example, exponentially faster than with classical computers. But we want to go beyond of this type of cryptanalytical applications. What can we expect that quantum information science will bring to the future battlefield, in particular in the areas of sensing and communications? So in this talk, I will describe recent theoretical research that we have performed that suggests that under certain conditions, quantum information science and technology could improve radar, underwater LiDAR, and underwater imaging, submarine communications, and gravimetric techniques. Now, I'm talking about the future, so there are many scientific and technological challenges to remain to be solved so these ideas can become a reality. So there is still extensive theoretical and experimental research that has to be done before all these ideas actually become a reality, but I believe it's important to start thinking about these things. So I'm going to talk about standoff electromagnetic quantum sensing, underwater communications, quantum gravimetry, and finally my conclusions. So this is Tanner. Later on, he will go into a little bit more detail about entanglement, but this is the main point of quantum entanglement. Let us define, this is the only pair of equations that I will have in all my talk. Let us define the mutual information of two variables, A and B, as the amount of information that we can obtain from variable A through the measurement of variable B. So now let's suppose that you have two systems and they are perfectly correlated, right? What this means is that the mutual information is equal to 1. Well, what is really wild is that when you use quantum systems, in particular when you have perfectly entangled quantum systems, the amount of mutual information is 2. And I know it sounds wild, but this is part of the strangeness of quantum mechanics. And it has been shown experimentally that actually the mutual information of an entangled state is 2. So it's double than the best that you can achieve with classical resources. What this means is that we could use this extra level of correlation to distinguish, for example, better between two photons, a photon that it's a signal photon and a photon that it's a noise photon. So we have this extra degree of freedom, this extra degree of correlations that can tell us when we have a signal photon coming back, for example, in the case of a radar, or when we are just measuring just a noise photon. So alternatively, you can think that we can hide the signal photons in the environment noise, and the entanglement correlations are the key to detect them. Now, I want to always to use the analogy that using entanglement is pretty much like cheating in a game of poker, in the sense that you are using marking cards, right? And these marking cards, these markings are actually the entanglement correlations, and your cards are the photons. So because they are marked, they have this special mark by quantum entanglement, then you can distinguish which one are the good cards. So this is our theoretical concept of a quantum radar. And basically, it's a system that generates an entangled pair of photons, which, as I mentioned before, they are perfectly correlated, and actually they have the double amount of mutual information that the best classical correlation possible. So one of these photons is stored somewhere in a quantum memory. The other is sent towards a target. This photon, it has to traverse an attenuating environment, so it may get absorbed, it may be scattered. So most probably, if you just do this one time with one entangled pair of photons, most probably you will get nothing. That photon will get lost, and you will never see it again. So you have to repeat this process multiple times. We estimate that you have to do this about 10 to the 9 times, which is a huge amount of times that you have to do, for example, in 1 millisecond. So this is one of the big challenges of realizing a quantum radar. But once you send your entangled photon, one you keep, the other you send, and if this one manages to come back, then you can use the entanglement correlations to help distinguish what you are measuring here, to know that the one that you are measuring here, it's a noise, it's a signal photon or a noise photon. And then you can use this extra amount of correlation to get more information about the target. And this is really the advantage of using a quantum radar. So here we're plotting the detection probability, where we define probability detection 1 when you have complete certainty that you are detecting the presence of a target. And detection probability 0, we're defining it as you have the same probability of determining that the target is there as if you make the flip of a coin, right? And this is the signal-to-noise ratio. So you can see the blue line is classical radar, the red line is a quantum radar with entanglement. You can see that if the signal-to-noise ratio is very, very high, both of them, they perform pretty much the same, and you have certainty of detecting the target if the signal-to-noise ratio is very high, which means that you have a strong signal or very little noise. On the other hand, if the noise is very high or your signal is very low, both of them, the probability of detection will be 0, which means that you will not get any information at all. However, you can see that the advantage is here around 3 decibels, where you can have a substantial advantage of a quantum radar because of this extra degree of correlation. And for example, even at 0 decibels, you have a substantial detection probability of 0.6. When you are using a classical radar, pretty much the detection probability is practically 0. So this is the real advantage of using entanglement. We can be detecting things even if we're working at 0 decibels. So this means that you can detect things that are farther away, or your adversary will have more trouble detecting your own sensing signal, or it will require to your adversary to use much more energy to jam your system. So these are some of the advantages of having a quantum radar with entanglement in the small SNR regime between -5 and 10 decibels. As I mentioned before, you will have higher target detection probability, even at 0 decibels. It's more difficult to detect by the adversary, so you can have stealth sensing. It's more resilient to jamming. You can have improved synthetic aperture radar imaging quality. You can have improved detection through clutter. And amazingly, the targets present larger cross-sections, which means that a target will look bigger when it's illuminated by a quantum radar. A few years ago, in 2014, I organized a workshop at NRL because I realized that the quantum radar, it was not a pie in the sky, even though it involves a large number of sophisticated technologies like quantum memories, generation of entanglement. I saw that there was someone somewhere in the world working on this specific problem, even if they didn't know that what they were doing in that moment could be used to develop a quantum radar. So the point of all this is that this is not a pie in the sky. I'm not using imaginary components. Everything is there. It's not sufficiently developed like to implement a quantum radar. For example, the number of photons that you can generate in the microwave regime. It's very limited at this time. But we believe that all these technologies, they can evolve and mature in the future. Another application similar to quantum radar is instead of using microwave photons, we use the photons in the blue-green regime, which is the optical window of seawater. So we have shown that, for example, a submarine, when it's navigating on the Arctic, it has active sonars to detect the presence of the ice. And this is clearly a non-stealth type of navigation or collision detection system, because it has to start pinging with sonar to know the position of the ice. So one way that we have proposed, and we got a patent last year, is to replace the active sonar with this type of underwater quantum lidars that basically they work the same as a quantum radar. You generate a pair of entangled photons, you send one towards the environment. It may come back or not, you have to repeat this several times, and then you use the entanglement correlations to determine if there is a target or not. Another really interesting technique, it's called ghost imaging, and this can be done either with classical correlated light or with quantum correlated light. But of course, when you use quantum light, you have much better performance. Now, this is a really, really wild idea, because what you do is you generate these entangled beams of light. Most of the beam goes here to a CCD camera, and only a stream of photons go here to some target, and they are collected in a single photon detector. Then you use here something to correlate this information, and actually you get a picture here of the target. So the picture here, it's coming from this CCD camera of a target that was never in the field of view of the camera. It's just with a few handful photons that interact with the target that you can get an image of the target. So this is why it's called ghost imaging, because the camera, it's actually never looking at the object. So we have explored how to use this, for example, in the maritime environment when you want to detect objects in the ocean, like whales, or some other things. And you are limited by the absorption of the light, and you have a limited number of potential sensors. So what we determined is, by using this type of correlations, we did some numerical experiments, and we saw that if you have, for example, this image here, which is a famous image for image processing studies, when we use these techniques of ghost imaging with some reconstruction techniques, we get this image here. So we're getting these images in just a handful of photons, and you cannot see a perfect representation of the original image. But if you just want to know if there is a target or not, this technique works relatively well. And of course, our experiments were, we assume just classical correlated light, but we are currently working on the case of entangled light. And in this case, as I mentioned before, you can have certain advantages of using quantum entanglement instead of classical correlations. Okay, so later on, Jeff and Jerry, they will talk with more detail about quantum communications, but this is an idea that we developed a few years ago. One of the problems to communicate with a submarine is that electromagnetic waves in the radio frequencies, they do not penetrate water. So the way we're currently communicating with them, it's using BLF, and a few years ago, ELF, but now it's a death technology because it requires huge antennas for transmission and reception. And the problem with this is that it's severely limited in bandwidth. So for BLF, you can transmit around 300 bits per second if the submarine is at 100 meters deep, and only a few characters per minute for ELF. And you require very cumbersome buoys and towed antenna arrays, and you require the submarine to take a specific course on speed alteration. So it's a really sophisticated way to communicate with a submarine. However, if we are using an optical channel, we have certain advantages over the cumbersome and bandwidth limited VLF and the now defunct ELF communications. So in particular, we show that if we use biologically inspired quantum photodetectors, which is basically photodetectors inspired by the quantum processing photosynthesis, we could allow very efficient classical and quantum communications in the optical window of the seawater across the water column of 100 meters and then towards an airborne platform. So our theoretical models predict that you could have an unconditionally secure key generation rate of 170 kilobytes per second at 100 meters deep in Gerloff type 1 waters, which means clear waters, which is about 600 times improvement over BLF. Unconditionally secure, as Jeff will talk later today, what it means is that it's completely independent on the computational resources of your adversary. So it doesn't matter how much computational power or theoretical models your adversary may have, he will not be able to break your key, at least in theory. And finally, I will talk about quantum gravimetry. Just consider a qubit, which is a unit of quantum information. It's usually represented with the intrinsic spin. Now, a bad way to describe what spin is to say that spin is the intrinsic angular momentum of a particle. That's formally wrong, but nonetheless, it gives a good idea of what's spin. You can imagine, for example, an electron which is rotating. And of course, formally, this idea is wrong. You have to formalize it. And it only makes sense to formalize this idea within the context of relativistic quantum field theory. And then you have that the spin is intrinsically connected to special relativity. And once you have that the spin is intrinsically connected to special relativity, then clearly the spin is also connected to the general theory of relativity of Albert Einstein that defines how gravity can be understood as space-time curvature. So the bottom line is that these qubits can be understood, or they behave as if they were gyroscopes under the presence of a gravitational field. So a quantum computer is basically this set of small quantum gyroscopes that you can manipulate independently and make sophisticated operations with these gyroscopes. In particular, you could use this quantum computer to amplify the effect of the gravitational interaction. So it has been shown that if you have a qubit in orbit, the qubit, which is a unit of quantum information, Tanner will describe in more detail what's a qubit. This qubit gets a small rotation, it gets a small change, and it's very small, but inside a quantum computer, it's possible to amplify this signal. So this is our idea that we call Wigner gravimetry, which is basically to use a universal quantum computer to measure gravitational fields. So one wild application of this is imagine that we have a noiseless, which is a big if, a noiseless quantum computer, right? So you have perfect scaling and you have the universal gate model. So now let's suppose that we have a very simple gravitational model for a submarine, in this case, the Virginia-class submarine. So you can see that the mass distribution in a submarine, it's not uniform. It's heavy towards the back because you have the engine and the reactor, and it's heavy towards the front because you have the missiles and the sonar. But right here in the middle, it's mostly air. So these things, we can model it in a very crude way, as if it was this asymmetric dumbbell. The interesting thing is that when you have this non-uniform distribution of mass, you have a non-zero quadrupole moment. So the monopole moment, this is just like in electrodynamics. The monopole moment of a neutrally buoyant submarine is compensated by the force provided by Archimedes' principle. So in a way, the fact that the submarine is neutrally buoyant, it means that its monopole gravitational signature is being hidden by the Archimedes principle. However, the quadrupole contribution, that's not compensated by Archimedes principle and could in principle be detected. So of course, because it's a quadrupole moment, it's much smaller than the monopole moment. And what we have here, this is the intensity of the gravitational field produced by a submarine, and this is the distance. So this is the monopole, and this is the quadrupole. So you can see the quadrupole is much more weaker than the monopole. And if we use the best known gravimetry technique known today, which is heavy atom interferometry, the limit is about here. So you can see that you could detect this in about, like 50 meters. So really, this technique is not very useful to detect a submarine, which could be at least 100 meters away from you. But if we use this type of Wigner gravimetry techniques using quantum information, and you have 100 noiseless qubits, which, as I mentioned before, it's a big if, then you could, in principle, detect this submarine at around 200 meters. And then this is exponential scaling, so you can go to really big lengths very quickly by increasing your qubit length. So this is 100 noiseless qubits. In reality, it's very difficult to have noiseless qubits. So if we have noisy qubits, of course, discounting will be off, right? But it gives you an idea of the power of quantum sensing and quantum computation. Okay, so these are like the major challenges that need to be addressed before all these ideas can become a reality. First, we need improved mathematical frameworks to describe quantum information in such a way that can be easier to understand for the non-quantum expert. And Tanner will talk in more detail about these issues. Then, for quantum radar and LiDAR, for example, we need a fast and efficient generation of entangled qubits, either in the microwave frequencies or in the optical frequencies. We need improved microwave single qubit detectors. We have very good detectors in the optical window, but not in the microwave. We need very reliable quantum memories, which are actually being developed within the context of quantum computation, for example. We need efficient and fault-tolerant quantum hardware that can make all the operations necessary so you can make your sensing and your communications. You need improved quantum signal processing techniques. Obviously, this is a completely new paradigm, and you need new ways to do signal processing. And similarly, you need new data fusion techniques. And finally, you need also better understanding of the qubit target and qubit environment interaction. And these are just a few of them. Notice that all these challenges to do things that are clearly with a clear military and intelligence application like radar, LiDAR, gravimetry, all these challenges, they actually being developed by the Chinese when they are making this space satellite to work. So even though the satellite is just designed to do QKD, many of these technologies are being developed there that could be transitioned to something more dramatic like quantum radar or something else. So this is my personal story of how we are actually living in a race between our country and the Chinese trying to develop novel quantum information technologies. A few years ago, I published my book, Quantum Radar. Some of you have read it. And if you haven't, you don't know what you're missing. Stephen King wishes he had written this book. So I wrote this book. A few years later, the Chinese bought the rights to the publisher. They didn't make a pirate copy. They actually bought the rights, made an official translation of the book. And my publisher, he was really surprised because he told me, this is very, very unique, because usually when the Chinese bought the rights for the publishing of a book, usually the author is of Chinese origin. For the record, I'm not of Chinese descent, if there is any doubt about that. So he said, maybe they are having a project, developing a project, and they want lots of people to learn from this book. Anyway, a few years later, I wrote my book on underwater communications, which is the book where I basically put forward the idea of underwater QKD, submarine communications using quantum channels and so on. And guess what? A few years later, the Chinese bought the rights and they published the book and the same story. So a few years later, I wrote my book on quantum information in gravitational fields. And you can see a pattern here, right? A few years later, the top Chinese scientist states that, wow, gravity is very important for quantum information technologies. So they still haven't bought the rights of this book. But you can see here a pattern moving on. Okay, so now let's look at what the Chinese have been doing actually experimentally, developing technology. They were involved in the long-range entanglement experiment, which was, on its time, really groundbreaking, doing entanglement between La Palma and Tenerife in the Canary Islands. So they were involved in this experiment. Years later, as I mentioned, they developed this satellite. Now they are doing QKD across 2 ground stations. And then recently, the official defense contractor of the Ministry of Defense of China, they announced that they had built a quantum radar and that they were able to detect stealth planes. I doubt that, but that's what they are saying. Nonetheless, which means is that they are doing work on this topic. And also, for your information, not only the Chinese are actually doing experimental work on quantum radar, but also the Europeans, they have a large program that they are just starting on quantum radar, and also the Canadians. So they made those claims. We don't know if they are true or not. A few years later, or a few months later, they started to do experiments on QKD, quantum communications underwater. All of these, clearly, they have been based on my books because they are where I first proposed these ideas in the, at least in the open literature, right? And so they are doing some experiments on quantum communications in the water. I wouldn't be surprised that soon they will actually be doing really QKD with an underwater vehicle. And maybe in the future, I don't believe their claim that they have a fully functional quantum radar, but probably in the future they may have one. And who knows, in the future they may also have the ability to do gravitational detection of our submarines. So to conclude, we have reason to believe that quantum information may well be the atomic bomb of the information era. Now, I presented a series of examples of things that we have been working on. And as I mentioned before, this is just theory, and there are many theoretical and experimental challenges that remain to be solved before these technologies can become a reality. But I think that these are high-risk, high-payoff endeavors. They are high-risk because, yeah, sure, it may not work at the end, right? We don't know. But it's high payoff because if we can do it and we can build, for example, in the future a quantum radar, then it means that we can do radar detection even at 0 decibels, right? So just think about the implications of doing sensing at 0 decibels. So we certainly believe that they deserve further scientific and engineering consideration, research, and discussion. Now, I have been talking about quantum radar, quantum LiDAR, quantum communications, quantum gravity, right? So it's basically just my classical mind trying to translate classical concepts into the quantum world, right? When I was working on quantum radar, one time someone in my chain of command, made the joke that, well, Marco, are you just going through a Skolnick book on radar? And yeah, the answer is yes. I have just been going through classical technologies to see how they could be transitioned to quantum. But certainly, we're just touching the surface of all this. Like Joe mentioned, imagine yourself when in the first years of the development of the transistor, just to think that this technological development could lead one day to the internet, right? Something that probably no one could imagine back then. I believe that there are many other radical concepts that we cannot even imagine at the present time. Right now, it's debatable, but probably we are not at the forefront of QIS. The Chinese clearly are ahead of us, at least on this part of satellite transmission of entanglement, QKD. And as I mentioned before, all these technologies, even though they are doing very innocent QKD, they could be easily weaponized and transition into more radical military technologies in the near future. So the question is, given all this that I told you, can we risk a QIS strategic surprise in the future? And that's something for you to think about. Thank you. Yeah.
We will have a panel session later where you can ask more substantive questions, but if there's anything of a clarification nature from our speakers, please ask them now, and we'll defer the other ones till later. Any questions? Clarification? Yes.
Hi, my name is Heather Spence. I'm a AAAS fellow at the DOE's Water Power Technologies Office. And I'm just interested to know, to what extent do you think implementation of these underwater technologies are power or energy limited?
Oh, that's actually a very good question. And depending on the type of entanglement technology that you use, it can be shown that you can actually have savings in power. You can reduce your power and do the same type of sensing as with classical means. So another way to see it is you can use the same power and have larger range, or you can use less power and have the same range. So yeah, it could save on energies. And with Jeff, we worked a few years ago on some ideas of spaceborne quantum radar. And the advantage of that is that one of the key deciding factors on what to put in a satellite has to do with the weight and the amount of energy that it will consume. And we estimate that using a entangled-based quantum radar could have a quadratic improvement in terms of energy.
Thank you.
Mm-hmm.
Well, thank you, Marco.
Thank you.